So where did definite integrals come from? Definite integrals came from wanting to write an expression for the area under a curve. So we drew the area that we wanted to find, we drew the region that we wanted to find the area of, and we tried filling it in with rectangles. And there was a time where we said, okay, well, we could just approximate the area by adding up the areas of a bunch of rectangles that sort of fill it up. Maybe they don't fill it up perfectly. And then we said, well, if we could take the limit as the number of rectangles went to infinity and the width of the rectangles went towards 0, if we could take that limit, if it existed, then we would find the actual area under the curve. So remember what a definite integral is then. It's a summing up of an infinite number of products. So in that example, the product was length times width to give the area of a rectangle. So let me blow your mind here. I'll quickly remind you that when you were in geometry, you learned that you could find the volume of a prism. A prism has a base and then has the same shape all the way up. So that is an approximation of a rectangular prism. You could find the volume of that prism by finding the area of, for example, the bottom or the top, so the area of one of the bases, and multiplying it by the height. We can find the area, we can find the volume of a cylinder by finding the area of the bottom, which is a circle, pi r squared, and multiplying by the height. So area times height. In this case, it would be pi r squared times height. If you remember any time in this, back in the related rate section maybe, that we needed the volume of a cylinder, it was pi r squared times h. So this is a product. This is a multiplication problem, area times height. And I can use this idea, plus everything I know about definite integrals already, to model adding up infinitely many volumes. So the reason the area under a curve problem worked is because you learned in geometry you can split up an area into a bunch of smaller sections and add all the areas together to get the whole. Well, volume is additive like that too. I can cut up a solid into as many different pieces as I want, add all those smaller volumes together, and get the volume of the original. So, imagine a roll of quarters. We're going to stick with this cylinder example. I could find the volume of a roll of quarters by finding the volume of each of the individual quarters and adding them up. So think of what Riemann sum I would write. And you can see I've written it here. So the volume of the roll of quarters is going to be the sum as the quarter number goes from 1 to 40, because there's 40 quarters in a roll. You'll know that once you go to college. And I'm going to add up a bunch of products, and the product is going to be the area of the face of a quarter, which is a circle, so the area of a circle, pi r squared, times the thickness of the quarter. So look how similar this is to the Riemann sums that we wrote back in chapter 5. Right, so you could change the number of quarters in your roll. You could change the thickness of the quarter. Maybe we're going to change from quarters to dimes. The same process still holds and would give us the volume of the roll of coins. So other things to notice, the Riemann sum that we wrote back in chapter 5, it allowed, really we were looking for the area under the velocity curve. And it worked even if not every rectangle had exactly the same area, because the height of the rectangle kept changing because I had a velocity that was not a constant. Well, the same thing works here. As long as I can write an expression in this form, a Riemann sum, so it is summing up a sigma of an area of a face times a thickness. Even if the actual area of each face is different, as long as I can write an expression like this, I can use a Riemann sum, and therefore a definite integral, to model the volume of a solid. So here we go, volumes by slicing. If you have a solid figure, so a three-dimensional figure, and you know you can write an expression for the area of a face of a slice. So imagine cutting through a roll of quarters and then turning it around to look at it. You're going to look at a circle. If you can write an equation for the area of that circle, and I know you can, I know you know it's pi r squared, then you can write an integral to give the volume of the whole solid. So in the format for that integral, it's going to be the integral from a to b, where a and b are x values, and then the area of the face of a slice, you'll need to write it as a function of x, and then the dx, that's going to be the thickness of each slice, so like the thickness of each quarter. In English, so it translated. If you can slice the solid in such a way that it makes it possible to write the area of the face, the area of the head-on view of the slice as a function of x, then you can write an integral for the volume of that solid. So there's 4 steps there. We're going to try them out. Let's see. On this example. Okay, I hope you like this. I'm trying here. Sorry that my face isn't in the picture, but I want us to have sort of the problem and a place to do the work at the same time. You can let me know what you think about this. So look at this. I have a region R, and just to clarify, the region R, it only counts up until x equals 4. I didn't actually shade it in, but that's the region I'm talking about. So imagine the picture cuts off after x equals 4. And the top boundary of that region is the line y equals square root of x. The right-hand boundary is the vertical line x equals 4. The bottom boundary is the x-axis, that's the line y equals 0. And I've been told that every time I cut into this solid, it doesn't look like a solid. Your picture only looks like it's two-dimensional. And there's a big, solid, I don't know, loaf of bread shape coming up out of the picture. And I've been told that if I cut a slice of that bread, that slice has a face that's a square. So let's try this. I'm going to make this picture bigger to sort of give you an idea. So imagine drawing a slice. It comes up out of here. I'm trying to draw it with perspective. That's a square, but it's standing up. That's why I drew it tilted so it doesn't look like a square. So imagine taking your big cleaver, your big bread knife, and going whoosh, and then looking at the face of the loaf of bread. It's going to look like a square. So that's the part I know. Every shape looks like a square. And if I can write an expression for the area of that square, then I'm going to be able to write an integral in the format that I just showed you. Watch how easy it is. So I'm just going to write myself some notes. You wouldn't necessarily need to write these notes to get credit on the AP test. I'm going to sort of copy my picture over here. If I tried to draw a slice of that, and I know that's one side of a square, could I figure out the side of that square? Well, here's a better question. Do I know a formula for the area of a square? The area of a square is side squared. Okay, well, as long as I can rewrite that so it's a function of x, I'm going to have exactly what, I'm going to be able to do exactly what I did in that integral. So I'm going to ask myself, if I slice through the bread, and this is one side of the square that sort of sticks up out of the page, can I write an expression in terms of x for that, the distance across that, the distance down that line segment? And I think it is, because I know that this, there's the bell. You guys are very patient with me. Thank you. I hope that doesn't freak you out. So that's x comma y, but I know y is equal to square root of x. And then the bottom down there, that's x comma 0. And no matter where I draw my vertical line segment, the bottom part of it, the y coordinate at the bottom, is going to be 0, because every one of these slices is going to touch the x-axis at its bottom. And it's going to touch the line, the curve, y equals square root of x at its top. So the distance across that line segment is square root of x. So a equals, the side of the square is square root of x, And I know to get the area of a square, I have to square the side. So don't expect it to always be this easy, but this one's not so bad. In this case, the area of the square, square root of x squared. You could simplify that to get x. So can I write my integral? Yeah, my integral is going to be this easy. Do I know my leftmost x and my rightmost x? My leftmost x is 0, and I've been told my rightmost x is 4. And this is supposed to be a of x times dx. You could write that in if you want. That's going to be the integral from 0 to 4 of x dx. You know what? Just for clarity, there's nothing incorrect about what I wrote, but let's just say, to help us see the progression, that's the same as saying the integral from 0 to 4 side squared is going to be radical x squared dx. So that can help you make the connection between the area of a square, which is side squared, times the thickness. So area times thickness. When it's time to evaluate the integral, you're going to have to simplify that. The integral from 0 to 4, square root of x squared dx. That's going to be the integral from 0 to 4 x dx. So to evaluate that integral, I need an antiderivative for x. That's x squared over 2, evaluated from 0 to 4. That's 4 squared over 2 minus 0 squared over 2, which makes final answer 8. All right, so I put my face back in. We'll try this next example. So we saw this problem in the last section when we were trying to find the area between curves. So notice how the same question, the same problem, I have a different kind of question here. I've been asked to imagine that I have a solid. If you sit it in the table, sit it on the table, it takes up the R space as its base. It touches the ground at region R. But it's a solid, and it's got, if you sliced into it, again, not that the only shape in the world is squares, but here the slices, again, I've been told, are squares. So, and notice here they've been very specific, cross sections perpendicular to the x-axis. That means the distance across the x-axis is going to be my dx, a very small change in x. So if I can write an expression for the area of this square, then I'm going to be able to write an integral for the volume. And you already, in part A, or B, whichever it was, wrote an integral for the area of R. Remember what you did. You found the integral from left to right of top minus bottom. And just notice the similarity here. Every time I draw a rectangle in, well, every time I drew a rectangle in doing part A, the top part of the rectangle got cut off by this g function, and the bottom of the rectangle touched the f function, so I knew that distance for the height of the rectangle was always g minus f. Notice here that's going to help us too, because the side of every square in this case is going to have that distance g minus f. So am I going to be able to write an integral? You bet. I'm going to integrate from left to right, so from 0 to 2 of side squared dx. That's just an intermediate step to help me make a plan. You have no obligation to write that. We haven't even defined what S means. But in my head, I'm thinking the area of a square, I'm going to take the side and square it. So as long as I can replace that S squared with an expression in terms of X, I'm going to have an integral, because look, all I had to do was write but do not evaluate. That's going to be the integral from 0 to 2 side squared dx. Well, the side of the square in this case, it's that horizontal, no, it's that vertical distance, top minus bottom. In this case, that was the g function minus the f function. That gets full credit. That's probably 2 points for writing that integral right there, and you have no obligation to simplify it. Notice you could write out the g function and the f function, but if you failed to put the f in some kind of grouping symbol, notice there's a subtraction here and an addition that would not be getting distributed. It would not get full credit. So you can write this to get full credit, or you can write out the two functions, but make sure the second function, the function that happens after the subtraction, goes in a grouping symbol. Final answer.